Now let's look at another thing. Okay, so latch based design is also difficult. Okay, latch based design is also difficult. Why? The reason is this: during the clock is 1, your D is getting out into the queue. Okay, but remember our sequential circuit like top level concept, like some combinational part producing a result at the iteration t plus 1, and that part is getting stored for the next iteration. Now see, let's imagine this somewhere on the outer side combinational circuit. I am trying to store a partial result through using this D-latch storage. When we can store it only when C is 1, but with this part, your D logic will immediately reflect onto the output. Remember that output, which was marked as GT in our that conception slide, GT, it immediately kind of corrupt the GT and get a feedback into my combinational part of the circuit. So it's very risky situation. Your whole circuit with the latch can become very unstable and just throw itself into a cycle of repeated cycle of 0 and 1 with some extra measurement. All right, so that's the reason why we want to go further complicated storage element, which makes sure at the iteration t plus 1, gt plus 1 is not going to corrupt my gt at that iteration. Gt plus 1 will only appear at the other side of the storage when my iteration is going to be gt plus 2. Okay, so it's kind of pushing it to the future. It want to make sure it only appear this partial calculation in the future iteration. Okay, so that's the reason we are going to go with the D flip-flop. Now D flip-flop we use on the input side we use a D latch, and output side we use a SR latch. Why? Because by construction of the D latch, it is always guaranteed that SR latch won't go into a rest condition. Why? Because D latch guarantees its output are always with the inversion condition. If this out y is, let's say we mark it as a y is 0, y bar will always be 1. That terminal will be 1. If y is 1, the other terminal will be always 0. That means this SR latch is guaranteed to not have a rest condition. So that's why we can use a SR latch instead of a D latch to reduce number of components, make it a little bit faster, and so on and so forth. Now what happens here, when C equals 1, okay, your D transfer to the Y, okay, but at this very moment, this C, same C, goes through the inversion for the SR latch part of it, right? So when C is 1, you are transferring this value of the D to the Y, but this Y value won't be transferred to the Q because your control for the SR latch is 0 that point, because it is going through an inverter. When now C equals 0, so no more new input, even if D changes, it won't reflect into the Y, but this Y, whatever we stored in the when C equals 1, Y will now go into the Q side. Okay, so we kind of make sure we separate the transfer of the D to Q at least by half cycle. And that means it is like you can well imagine we are actually walking towards like declaring C as a control to C as a clock. so we just introduced a cycle, right? Half a cycle, it actually makes sure D is not reflected on the Q immediately. It stops it for at least half cycle when your C transition from 1 to 0. So this is what happens. This is what we call a negative edge trigger flip-flop. Okay, so let's just cover up all the internal details, and we have one D latch with D C Y Y bar and one SR latch S C R Q Q bar, and the clock, this C is connected to the clock, and clock is inverted, and that inverted clock is connected to my SR latch. Now we call it, this whole component we call a negative edge triggered D flip-flop. Why? Let me explain it. So clock as a signal, it is always like going up and down, is repeated in a period. Okay, and now let's say D is kind of independently like just toggling its logic value. We don't have, let's say, any control over it. Now you see at the Q is not following the D, right? Q value is changed here from 0 to here, and then also here, but in between we have a lot of changes on the D. So all the values of the D, even if it goes up, down for some noise or something like that, it really doesn't matter. What matters is this: when C or clock become 1, your Y is going to the 1, right? That D is transferred to the Y, and then next C will go down, it will be closed. So what will happen during when CLK stays at 1, you see that D goes down in between, so immediately that value gets reflected on Y, right? And then again it goes up somewhere. At this point Y goes up because now C is 1, but before C goes down to 0, D goes down to 0 before that, so it reflects immediately back on the Y. And then at this point, C equals 0 for the D flip-flop, but D changes, so it is not reflected back on the Y, right? So we stay, Y is staying at 0, and then sometimes D goes up when clock was 0, but clocks also go up. At that time your Y goes up, and then when the clock goes down, D is still up, your Y still is up. Then in some point of time D goes down, but at that point your CLK is low, so your Y also stays at high because that value is not transferred. So you can follow through why the Y is not following D correctly, like, or exactly it is not following D. It is basically following for some part and following for other part. It really depends on when the clock is on or clock is off, right? Now come back to the Q side. Now Q will transfer something. So Y and S is connected, right? And Y bar S and R is connected. So this data will be transferred to Q only when clock is low, right? Clock is inverted, and that control signal is getting an inverted clock. Okay, so let's see. Y is 1 here. Y, so every low, let's follow the every low clock cycle when Y value will be transferred to the Q. So at this point your Y, this first so first clock, when it was low, Y was low, Q was low. Second low clock cycle, your Y was low, Q was low. Third low part, Y was low, Q was low. Now we can just follow through that part. Only during this, when the Q become high, you can see the Y was staying high during that time. when clock was low, so that is was reflected on the Q. And then Y goes down, C goes up, so nothing happens then, right? Basically, this data transmission or data handover between S and Q is just turned off when this clock goes to high, so it stays at high. Now next clock down, Y becomes 0, so it goes down. So you see, like, basically it is selectively passing the value of D onto the Q, and the condition is only when your D is staying sufficient enough on the high state of the clock onto that specific D flip-flop, negative edge trigger D flip-flop. It needs to stay high for the duration of the clock high. Only then low part of the clock will transfer that high value onto the Q, right? It's the same for the everything else. See, it is when it was staying low for the whole cycle here. See, at this point it stayed at the whole cycle, and then that fast transition of the Q into the low. Okay, during that D also stayed low for the entire high cycle, right? So that becomes low. So this is what the flip-flop does. It basically register a value, incoming value on the D at one of the clock edge and reflect that value to the next clock edge, the next negative clock edge. Like, let's say it's a positive edge, it is registering that value, and negative edge, it is reflecting back. Okay, so why it is called a negative edge trigger? Because if you see a relation between clock and the Q, any value changes on the Q happens only at the edge when clock is coming down from high to low state. So that's why it is a negative edge trigger flip-flop. We can have a positive edge trigger flip-flop, which is, by the way, usual. So positive edge trigger flip-flop, you will see that change in Q happens at the positive edge, means when the clock goes from low to high, at that point Q gets changed. That means your D get registered into that flip-flop at the negative edge of the clock. Okay, so that's the positive edge trigger D flip-flop. So I have one example where you can make it. One inversion goes to the C on the D latch, and another inversion you make to the C latch. Well, you can straight bring it to from the clock to C. I have introduced one more inverter just to make sure drive strength of the clock signal is not lost. That's why, but it can happen. You can just logically, at least, you can directly connect from clock to C on the SR latch side, and that will give you positive edge trigger flip-flop. You see that Q value changes only when clock goes from low to high. That means your data D get registered only when you are going at the low side of the clock, right? Only when low side of the clock that data get registered. So please follow through this timing diagram for both positive edge triggered flip-flop and negative edge triggered flip-flop, and study it carefully. Then you will come to know about the behavior of these flops. One more point, this specific configuration is called a master slave flip-flop. This first stage D latch is called master because all the value it basically allows or disallow based on the first stage, and second stage is slave. Whatever master is latched, that value will be reflected back through this SR latch part of the thing. So this part is called a slave. So this is a master slave flip-flop configuration. Now, now what we want to do is one more thing on top of that. So this positive edge trigger flip-flop or negative edge trigger flip-flop is okay, fine. It is storing a value 0 and 1, etc., etc. What is my power up value? Remember, we have to consider the Z0, the initial condition. So what is my initial condition here? Like if I power it up, where the Q value will stay? Answer to that question with this configuration, this circuit, logic circuit, we don't know. It can be either 1 or 0 depending on what's going on at that time of instance, right? It's depend on the ambient temperature, its humidity, this and that. Lot of factors goes into that. It will go and be there at some point. It hopefully it will be stayed at 0 or 1. We don't know, or it may even start oscillating. Like it just go between 0 and 1, 0 and 1, and start oscillating. So we need to make sure we have a initial condition, and to do that we can introduce something called a preset and reset onto this. And let's talk about this preset and reset asynchronously. Means without depending on the clock signal C, we can just preset the value Q to 1 or reset the value Q to 0. How we do it? We have one signal P, stand for preset, which goes to the master side and the slave side, and it becomes your 3 input. The back-to-back inverter become a 3 input NAND gate. Okay, we have one extra input into that. So we hold this preset value to 1 if we want to have a normal operation of this flip-flop. Okay. And as soon as I put a preset value to 1 and reset value to 0, reset is also going through a 3 input NAND gate. So what happens if P is 0, P is 1, R is 0, then what happens? R is 0, right? So it will put the Y bar value as 1, which will make the Y as 0, and also here Q bar as 1 and Q as 0, right? P0 R1, P1 R0. And if I put a P as 0, R as 1, then what happens? P will push the Y to 1 and Q to 1, and Y bar will become, since the R is 1, Y bar will become 0, and Q bar will become 0. So we are deterministically set the value of the Q bar and also internal Y and Y bar by setting P equals 1, R equals 0, or P equals 0, R equals 1. Of course, in this case, both setting to P equals 0, R equals 0 is a rest condition, and the normal flip-flop condition is you both keep P and R as 1, right? So if you keep both P as 1 and R as 1, then rest of the functionality of this circuit will depend on functionality of the rest of the logic combination. So that's my like non-preset reset condition. P is 1, R is 1. Okay. So what happens, like you remember, like at least for the old desktop and laptops, and also actually you have now the software way of doing it, there is something called a restart or reset in your computing system. What it does exactly, it sends out this reset preset condition towards the entire system to make it a known state element. Okay, to make the all the storage, all the feedback as a known initial condition point. So that's the function of your reset button on your desktop. Okay, it basically, and in every system, even if when you power up a system, the system sends out preset reset signals. That is the first thing any digital system does. Just go and make all my storage element to a known state. Okay, Z0, deterministic Z0 condition as my theoretical model of a sequential circuit. Okay, so that's my preset reset. So with the preset reset, usually we make it as a bubble of preset and reset, means your P 0 and R1 is my set condition, preset condition. So we usually make it an invert, right? 0 and 1. It is an inversion relation between them. So we mark it as a bubble. Means we very well know, like with this schematic symbol, we readily kind of infer if I set my P to 0, it is going to be a preset condition, assuming R is 1 that point. And if it is R is 0 and P is 1, then that's my reset condition. And if both are 1, that's my hold condition, and both are 0 is my rest condition. Okay. Now if I actually, in some diagram, if I just take out this bubble, it means just the opposite. Means if P is 1 and R is 0 is reset condition, P is 0, R is 1 is a reset condition, P1 R1 is a rest condition, and P0 R0 is my whole, like, normal operation condition. Okay, so we have now have a 1-bit storage element with preset reset. And also notice this little triangle on the clock terminal. So it's usually the symbol signifies that terminal is used as a clock. Even if you don't mark them, just a triangle, that terminal always, in any component, it serves as a clock terminal. Okay, it's a very special sign in the digital symbol. So that's all for this sequential like storage element discussion and sequential circuit theory. What is the model of it? Next time we'll discuss at least partly how from a problem statement we can design a sequential logic circuit. Okay, that would be the topic for the next lecture, lecture 7. So if you have any questions, send me email or ask me in class.